Problem 2, part 3 is essentially the same as problem 2, part 2, although this may not be obvious, but the statement to be proven is indeed essentially the statement you just proved. Let's see what's going on. We have these variables y sub I, which take on the value 1 with probability p, and 0 with probability 1 minus p. And we have a number of independent such variables, y1, y2, etc. And we string them into a big string of length n. Let's say we have n such variables, a big string of length n that we're going to call big Y. And we want to show that as n gets large, almost certainly a certain inequality is satisfied by big Y. Specifically, let's say a string little y is good or maybe a better word would be typical, but I've already written good. Let's say string little y is good if the probability that big Y equals little y is between 2 to the negative n, where n is the number of bits in big Y, times h of p, by which I mean p times log p plus 1 minus p times log 1 minus p, and my logs here are all base 2, plus epsilon and 2 to the negative n h of p minus epsilon. And now what we want to show is that as n gets large, the probability that big Y produces a good string approaches 1. Why is that? Well, let's rewrite this inequality. The probability that big Y equals little y is just going to be p, the number of ones in little y, times 1 minus p, the number of zeros in little y. But we want to show that this condition almost certainly holds of big Y, so I'll replace these little y's with big Y's, not that you can tell the difference with my handwriting. And we want to show that this is between 2 to the negative n h of p plus epsilon and 2 to the negative n h of p minus epsilon with probability 1 as n gets large. Let's take log base 2 of everything here. So we want to show that number of ones in y times log base 2 of p plus the number of zeros in y times log base 2 of 1 minus p is between negative n h of p plus epsilon and negative n h of p minus epsilon. Well, let's say x sub I equals log base 2 of p if y sub I equals 1 and equals log base 2 of 1 minus p if y sub I equals 0. Now what we're showing is that the sum of x sub I, that's what this whole left-hand side here is between negative n times h of p plus epsilon and negative n h of p minus epsilon, with probability approaching 1 as n gets large. That's the statement we have to show. Another way of phrasing it is that sum of x sub I minus n times h of p is between negative n epsilon and n epsilon. In other words, if I take this sum and divide it by n, the magnitude of that result is less than epsilon. We want to show that that condition has probability 1 as n grows large. Well, this condition amounts to the same thing as saying the average of the x sub I is no more than epsilon from h of p. And now finally, we can observe that the law of large numbers guarantees this will have probability 1 as n grows large, because h of p, which is p times log p plus 1 minus p times log 1 minus p, is equal to the expected value of these x sub I. And the law of large numbers tells us that if we take the average of a number of variables drawn from the same distribution, then that quantity's deviation from the mean of that distribution has probability 1 of being less than any particular epsilon in the limit as the number of variables goes to infinity. So what we've done here in part 3 is exactly the same as what we did in part 2, although it's sort of obfuscated by the fact that we've raised 2 to the n to things and so on. But this is all exactly the same as what we just did in part 2. I've just rewritten it.